Hi there. So last time we looked at integration. In particular we looked at integration of common functions like exponentials and trig functions. We also looked at definite integrals, and we also finally looked at integration by substitution, which we use when we have a function inside another function. This week we're going to be looking at integration by parts, and then following that we'll be looking at double integration. Okay, so first up is integration by parts. So when do we use integration by parts? Well, essentially we should use integration by parts when we are trying to integrate a function that is made up of two separate functions of x being multiplied together. So it's almost equivalent to the product rule for differentiation and can actually be derived from the product rule for differentiation. So the product rule for differentiation is shown here in this blue box. So if we want to get a rule for integration by parts, then we actually have to rearrange this equation and then integrate both sides. So the first thing we do is that we rearrange to find this term. So we can write that u times dv by dx will be equal to duv by dx minus v du by dx. We then want to integrate both sides of this equation, and we want to integrate with respect to x. So we can integrate the left hand side, and then we have to integrate each term on the right hand side. Okay, both sides get integrated with respect to x. So looking at these terms, we can see that dx will cancel on each term. So what we're left with is the integral of u with respect to v being equal to, well, if we integrate a differential of uv, then we just have uv, and then we have minus the integral of v du. And that is our rule, our overall rule for integration by parts. So to see how we can actually use this, let's take a look at an example. So here we're being asked to integrate x multiplied by sine x, and we're going to integrate with respect to x. So to use integration by parts, the first thing that we need to do is to establish what we're going to let equal u and what we're going to let equal dv. So here let's say that u is equal to x and dv is equal to sine x. If we look at our rule for integration by parts, then we're also going to need an expression for du and an expression for v. So to find an expression for u, we can say that du by dx is equal to 1, so du is equal to dx. To find an expression for v, we can just integrate dv, so v will be equal to the integral of sine x with respect to x. Hopefully you'll remember that the integral of sine x is minus cos x. Okay, so now we have all of our terms that we're going to need to carry out integration by parts. So what I like to do to keep the sort of terms all separate from my main working is to just put a little box around it so I don't get muddled. So now we can say, if we look at our formula for integration by parts, that the integral of u to v will be equal to u times v, so x times by v, which is minus cos x, minus the integral of v, which is minus cos x, with respect to u, so du, which is equal to dx. So we can then say that we have minus x cos x, and then we can do the integral of the minus cos x will be, hopefully you remember, minus sin x, and then we've got our constant of integration as well. All that's left then is to just tidy this up a little bit. So we can say that we have minus x cos x plus sin x plus c, and that's our final answer. Let's take a look at another example. So here we're trying to integrate 4x multiplied by e to the power of 3x with respect to x. So again, the first thing that we need to do is set up what's going to be equal to u, what's going to be equal to v. So here we'll set u equal to 4x and v equal to e to 3x. So then we can say that du by dx will be equal to 4. So du has to be equal to 4 times dx. To find an expression for v, we can integrate the v, so integrate e to the 3x with respect to x, and we get, again, hopefully you remember, we get 1/3 e to the 3x. We can then draw a box around that, and that's what's got our terms that we're going to need. So we can then go back over to look at our original integral, and we can say that that's going to be equal to u times v, so 4x multiplied by 1/3 e to 3x, minus the integral of v, which is 1/3 e to 3x, with respect to u, which is du, which is then equal to 4 dx. Okay, so to simplify that, we can say that we've got 4/3 x e to the 3x minus, or we can take the 4/3 out of the integral here, and we're left with the integral of e 3x with respect to x. So then we can say that we have 4/3 x to the 3x minus 4/3 times, well, the integral of e to the 3x we've already done is 1/3 e to the 3x plus c. Again, all that's left then is to tidy this expression up. So we can actually write this is equal to 4/3, and we can take e to 3x out of both sides, and we can take the 4/3 out of both sides, and we're left with x minus 1/3. And then you've got your plus c at the end as well. So that's our final answer for that example. Do try where possible to tidy up your final answers. It's really sort of best practice to do that. So we're now going to look at an example that's actually quite similar to the last example, because we have 3x being multiplied by e to the 5x. We're integrating with respect to x. However, now we have a definite integral because we have upper and lower limits of integration. So we kind of start this problem in the same way as we would for an indefinite integral. So the first thing that we want to do is set out what equals u and what equals to v. So here we'll let u equal 3x and v equal e to the 5x. So then we can say that du by dx is equal to 3. So du must be equal to 3 times dx. To find the expression for v, we simply integrate v with respect to x. So v is equal to 1/5 e to the 5x. So we can then come back over to the left hand side and actually lay out our integral here. So this expression is going to be equal to u, which is 3x, multiplied by v, which is 1 over 5 e to the 5x. And that term we're not actually going to do anything to it, so we can just pop it in the square bracket with the upper and lower limit of 2 and 0. From that we're going to minus the integral. Again, we've got our upper and lower limit of 2 and 0 of v, which is 1/5 e to the 5x du, which is 3 dx. So here you can tidy this up a little bit by saying that we have 3 over 5x e to the 5x. Again, we keep that in the square bracket for just now with the upper and lower limits. Minus, well, we can take the 3 over 5 outside of the integral. That leaves us to integrate e to the 5x with respect to x, which we know is 1/5 e to the 5x. And we can put our upper and lower limit of integration on there as well. So we can then bring all of this into one big square bracket with the upper and lower limits. And we can tidy up a little bit by saying we've got 3 over 5 e to the 5x multiplied by x minus 1/5. And we can put all of that in our square bracket with our upper and lower limits. All that's left now is to substitute in first x equal to 2 into this whole term, which gives us 23788.58 in total. And from that we're going to minus, well, when we set x equal to 0, which gives us minus 0.12. So we have a minus, which becomes a plus. So our final answer is then 23788.7. And that's our answer for that example. So before we move on to look at double integration, I just want to point out how integration by parts can actually be used to find the integral of the natural log of x with respect to x. Last week we talked about how we didn't have a sort of straightforward rule to do this, so we do need to use integration by parts. So to use integration by parts here, we can let u equal the natural log of x, and then we have to then let v equal just 1. So we can then say that du by dx, if we differentiate the natural log of x, hopefully you remember that we get 1 over x. So du is just equal to dx over x. If we're going to integrate the v, so we're essentially integrating 1 with respect to x, then v is just equal to x. So that's us got all of the variables that we need, and we can then go back over to the main integral. So this entire integral of log x with respect to x will then be equal to u, which is the log of x, times by v, which is x, minus from that the integral of v times du, and here du is equal to dx over x. So what happens is that these two x's actually just cancel out here, and what we're left with is x log x minus the integral. Essentially we have 1 here, so the integral of 1 again is just x, and we have our constant of integration. We can then just tidy that up a little bit and say that we have x times log x minus 1 plus c. So that's our answer for the integral of the natural log of x. So the last topic that we are going to be looking at in integration is double integration. So if we have a function of two variables, say x and y, then we can be asked to essentially integrate this with respect to each variable. What's really important about double integration is the order of integration. So here we're asked to find the integral of a function f, which has two variables x and y, and you can see here the x integral, the integral with respect to x, is on the inside, and we have the upper and lower limits of x on the inside as well. So when it's on the inside, we would integrate that first. Okay, integrate with respect to x first. And then on the outside, we have the integral with respect to y, with the upper and lower limits of y. So that's on the outside. So that means that we then integrate with respect to y last, after we've already integrated with respect to x. So to see what I mean, let's take a look at an example. So here we have a function which is 4x minus y, and we're asked to integrate that first with respect to x, as dx is on the inside, and then after that with respect to y, as y is on the outside. So first we are going to deal with the inside integral with respect to x, and then after we've done that we'll deal with the outside one. So the inside one, we have 4x minus y integrated with respect to x gives us 4x squared over 2 minus, well, we don't know what y is, so we can just treat it as an arbitrary constant number. So we have y multiplied by x, and that's our internal integration. And then we have upper and lower limits of x equal to 2 and x equal to 1. So if we want to pop in the upper and lower limits of x here, we can say that the 4 and the 2 cancel to give you 2x squared, so that becomes 2 times 2 squared minus y times 2, and we can put that in a curly bracket, minus, let's let x equal to 1, so you end up with 2 times 1 squared minus y times 1, and that gives you, oh, you have 8 minus 2y minus 2, and then the minus and minus come together to make a plus y, so we can tidy that up to be 8 minus 2 gives us 6, and minus 2y plus y gives us minus y. So our internal integral is equal to 6 minus y. So now that we have our inside integral being 6 minus y, we can say that our outside integral is going to be the integral of 6 minus y with respect to y, with the upper limit of 4 and the lower limit of 2. So if we can now integrate that, we will have our final answer for the problem. So integrating the 6 minus y with respect to y gives us 6y minus y squared over 2, and then in our square brackets we have our upper limit of y equal to 4 and our lower limit of y equal to 2. So if we substitute in our upper and lower values, we have 6 times 4 minus 4 squared over 2. Now you can put that in a curly bracket. Minus 6 times 2 minus 2 squared over 2. That then means in the first bracket we have 6 times 4, which is 24, minus 4 squared, which is 16, divided by 2 gives us 8. And that has a subtraction of the 6 times 2 gives us 12, minus 4 squared divided by 2 just gives us 2. So we end up with 16 in the first curly bracket, minus 10 in the second curly bracket, and altogether that gives us a final value of 6. So you would expect your final answer for a problem like this to be a numerical value. So that is one example of double integration. Just be careful that you sort of don't get muddled up with the inside integration and the outside integration, and the inside limits and outside limits. So in this video we've had a look at quite a few different examples of integration by parts, and also an example of double integration. So thank you very much for watching.